Now, what the program actually can do is summarized here. So we're going to start with the 3D reconstruction of tubular bodies. Then we're going to do mesh generation, finite element analysis, and derivation of patient determinants. These 3 points are limited to AAA, so abdominal aortic aneurysms, simply because this is specific data for this type of pathology. And then visualization and data management, of course, is general here. Now, the key in this type of simulation is that you have an accurate geometry reconstruction. And this software is using the concept of deformable bodies, and that's what you see here. A deformable model inflates within the body until it captures, in this case, the lumen, and successfully segments the lumen from the remaining anatomical information in the data set. Now, this concept is implemented through the principle of virtual work, and those people working with structural finite elements, this equation will look very familiar. So we have an internal potential and an external potential, and the key now to use this concept for image segmentation is that this traction, the external force that acts on your structure, is now a function of the image, and this is how this is implemented. And I here is the image intensity, and you have other parameters here. So if you're interested in that, this is available in the open literature, and you can read more about that. Now, the concept of deformable model has been implemented through a pre-segmentation using snake models. So that's a two-dimensional segmentation step where slice by slice the lumen or the exterior surface is segmented, and then we have the segmentation of the luminous surface and the final segmentation of the exterior surface by using a balloon model. So a balloon model is a three-dimensional active segmentation model, and you see such a model here. This is the lumen, and you can imagine that this is a balloon that inflates within your three-dimensional data set. Now, the key here is that the surface remains continuous, and we cut off small vessels which are not of interest to our structure analysis. This is very important in order to keep the model as small as possible, and don't include additional information which is not required. What you can see here, for example, is that we cut off the artery going to the kidneys here, because this is something we don't need in our structure. Now, in order to control this segmentation algorithm, you have different parameters available, and we're going to see that later in the live segmentation. And these parameters are predefined for small aneurysms. So if you're going to segment a small aneurysm, you will not have to touch upon these parameters. If you're going to segment something different, you have to find your set of parameters that fits your application. Now, image data is typically full of artifacts due to imaging limitations and whatsoever, and it's important that you have manual interactions available where you can manually interact with the segmentation algorithm. Otherwise, your result will not be as what you expect. Now, the most simple interaction is that you simply draw into your image data. If this is an artifact here, then you can basically overdraw these artifacts by using a three-dimensional pencil tool. Another option is that you set control polygons. So if this would be the segmentation and the outer surface is not there where it's supposed to be, so this here is the outer surface of the aneurysm, and the segmentation algorithm stopped for some reason here. So what you can do is, on selected slices, you can put the control polygon, and we're going to see how that works anyway later. Now, coming to the mesh generation, and the characteristics of mesh generation are itemized here. The wall and the thrombus are meshed separately with matching nodes, so you don't have to deal with complicated interface descriptions between these two bodies. The wall is hexahedral elements, thrombus is hexahedral dominated elements, And there are some features that the wall thickness depends on the thickness of the thrombus tissue, and other points here. What's also need to be mentioned is that it's easily to use an anisotropic description here, because we use an anisotropic mesh refinement. However, local mesh refinement is not possible. Now coming to the structure analysis. The structure analysis uses the finite element method. Here the wall is described by this hyperelastic function reported in Ragavan and Warp 2000, and the thrombus tissue is described by this hyperelastic function here, where this C is a stiffness parameter that depends on the radial position, because it's known that thrombus stiffness changes from the luminal to the abdominal part. Right, so what you have to do as a user is you predefine, so this patient parameters C, C1 and C2 are predefined, so you don't have to do anything there. What you then do is you prescribe arterial pressure, gender, family history, and so forth. Then you define the boundary conditions of your structure analysis, and finally you perform the structure analysis. And we're gonna again see how this works later. Now finally, data analysis and reporting. The final step of the software is that it runs through all this data which has been generated, extract geometrical determinants and mechanical determinants, and puts this into an illustrative PDF report. Key here is that it relates the individual patient to the mean aneurysm patient in order to get a relative rupture risk assessment.